In this lesson, we're going to be covering transmission media and transmission technologies. Network media is this transmission media that I mentioned in the title slide there. The media is the mechanism that carries the signal and data across networks from the source node, the sender, to the destination node, the recipient. So very often these are cables of some sort, and in our wireless networks, we actually use the air as the transmission media. But let's dive into this and let's talk about these different types of transmission media right up front here. One aspect of the media that we're going to be exploring deals with the efficiency of the transmission. In other words, how far will the signal go before it degrades so much we can't understand it anymore? And the second aspect deals with the security aspects of the actual signal conveying across the media. So as you look at these different media types, it's a good thing to have in your mind what is the more secure and more efficient transmission media and what is the lesser secure and lesser efficient transmission media. Recognize that more secure and more efficient is almost always going to be more expensive. And the weaker media, the types that are very prone to data theft and data corruption due to interference and static and things along these lines, this is generally your cheaper type of media. So there's always going to be this trade-off. So let's dive into these 5 different types of transmission media, and we'll understand a little bit more about them and how they operate. The first one on the list here is considered to be the most secure because it has essentially no emanations. In other words, it's very, very difficult for a bad guy to steal your data signal as it conveys through the fiber optic cable. And it also is a very efficient transmission mechanism. In other words, it can go miles and miles before the signal degrades to a point where the receiver can't understand it. So what fiber optic cables actually use is light pulses. In other words, it's actually photons that are carrying the signal and the data. So if you want to think of it in very basic terms, think of when the light is on, that's a binary 1. And when the light is off, that's a binary 0. And photons do not produce emanations. Now, what we're going to see in some of these later transmission media types is they use electrons to carry the data signal. Well, electrons have this phenomenon called emanation. And we'll dissect that in just a minute, but photons don't emanate. And as a result, they're considered to be the most secure. They are one of the most efficient media types, and therefore they're one of the most expensive media types. We get very high data rates on fiber optic cables, gigabits of data, and therefore it's a very good vehicle to carry your signal to use as you connect your locations together across the city perhaps, or even within an office. Now typically it's more expensive than we want to spend within an office. The next one down on the list is coaxial cable. Now coaxial cable has been around for a long, long time. It's actually commonly used in your homes to carry your TV signal into the home from the cable provider. It is a center conductor that actually carries the data signal, but then wrapped all the way around that center conductor is a grounded sleeve or shield that helps to keep the signal contained within the coaxial cable. Now, as it holds that energy within, less energy leaks out. Therefore, the emanations, the security component of emanations, is fairly strong. Difficult for a bad guy, not impossible though, but difficult for a bad guy to steal that signal without getting very close to the cable, perhaps even placing into the cable itself. Coaxial cable uses electrons and radio frequency waves on that center conductor to convey the data within the signal. And again, it's these electrons and radio frequency waves push electrons around. And as these electrons flow through the cable, they actually emanate an electromagnetic field around the cable itself, outside in the air around the cable. Now that grounded shield around the coaxial cable tends to keep that collapsed and contained within the shield. However, some will still leak out. So it has very good emanation protection. And however, it still is not emanations free like fiber optic cable. Now, there's another aspect of the emanations, and that is if I can emanate a signal outbound, that says other signals in the area that are emanating might actually induce signal, which is corruption and interference on my signal within the coaxial cable. So these emanations from other sources can actually penetrate into the coaxial cable and start to degrade my signal due to this interference. So coaxial cable is considered one of your better connection media for networks. The next one down on the list is shielded twisted pair, and its very close cousin, unshielded twisted pair. Now this is your standard Ethernet. Your standard Ethernet almost always uses UTP, or unshielded twisted pair. Now, these two are constructed approximately the same, other than the shielded twisted pair has a sort of an aluminum foil wrapping, a conductive wrapping around the wires inside the Ethernet cable. And it's called twisted pair because there are actually 8 wires inside these cables, and we take one wire that's going to carry the data signal and a second wire that is going to be grounded, and we wrap the ground wire around the data wire. In other words, we twist them together as a pair. Now, the grounded wire tends to disrupt this propagation of the emanated field around the data carrying wire. So as we're pushing a signal through that wire, we are using electrons to carry that signal, and those electrons, once again, propagate into the air. Well, again, the grounded wire that's wrapped around it will disrupt that magnetic field around the data carrying wire, and we have some marginal shielding, if you will, because of this grounded wire. Now, the shielded twisted pair is a little bit better as far as emanation security are concerned, but it is more expensive and it's fairly difficult to work with. If you're building these cables, it's a real pain to build these cables. The unshielded twisted pair, hands down, has dominated the marketplace when it comes to connecting your networks together. So the UTP is by far the dominant technology, network media, that's used for corporate networks. Now, a very popular, relatively new entry into computer networks as a media is wireless networks. It uses radio frequency electromagnetic waves propagated into the air, where the air is actually the media itself. And this means it is the least secure because it is nothing but emanations in the air, which means a bad guy with a receiver can listen to everything you're propagating across your network. That's why we have to take extremely high measures to secure our wireless networks. Because we don't have to buy cables and have cables run throughout the building, this is also the least expensive network media that we could implement as well. So it's very easy to assemble a wireless network. It's very easy to tear it down and move it, relocate it, etc. So the wireless networks are the least secure with nothing but emanations, but it is by far the cheapest approach when it comes to media because there's essentially no cost. We're using the air as the media. And again, as we said, these emanations allow for theft of data signal and also allow for inbound propagation of unwanted signal that tend to degrade the signal due to crosstalk and interference. Now, this term attenuation deals with a signal degradation over distance. We're going to look at that in just a few minutes. This lesson is going to cover several of the key terms that need to be understood about network media. So we're going to be looking at these definitions. Now, the first definition we need to address is a common problem with all network media types, and that's called attenuation. Attenuation is a naturally occurring phenomenon, and basically it is degradation of signal over distance. So as you have a longer cable and you are transmitting from one end of that cable at the source to a destination at the other end of that cable, the signal will degrade over distance. So the longer the cable is, the more degradation or attenuation there is with this signal. Now, we can make a cable so long that the signal is so degraded by the time it gets to the destination that the destination can't understand what the signal is saying. So we have to move back then to a shorter and shorter cable until we can be certain that the destination will always understand the signal, that it hasn't been degraded so badly that the destination can still understand what the signal is conveying, the data part of the signal. Now, this attenuation is due to several different types of phenomenon. The first one is called interference. This would be some sort of induced signal due to emanations from some other source. It might be a radio tower. It might be a wireless network. It might be a microwave oven that somebody's using in the break room. But electromagnetic interference in the air, it's all around us, is a source of interference. And if that signal that isn't wanted somehow finds itself on our wire that's carrying our data signal, that by definition is the interference. There's a phenomenon called impedance that is a component of high frequency data signaling. And if there is high-speed data, of course, on our corporate networks, that's what we want, high-speed data, we wind up with some sort of impedance characteristics or phenomenon occurring. Well, the impedance of the system must be very well tuned so that all components have the same impedance. And if there is some sort of mismatch, we wind up with an inefficient transmission through that area. Maybe it's a connector, or maybe the cable got cut and we had to solder it back together, some sort of splice. These are sources of impedance mismatch. And then, of course, as I said, if we have to put connectors together, the electrons running through our cable must jump from a pin on one connector into the wire on the adjacent connector, where these connectors squeeze these pin in the socket together. Well, this minuscule air gap, perhaps even microscopic air gap, is a source of signal loss. And they call this insertion loss. As the pin gets inserted into the jack, then we have this degradation or attenuation of signal. Now, the next definition down is interference. And as I said, interference is generally unwanted signal on your data carrying conductor. And it very often is induced by some sort of emanation from some other source. As we said, it could be a radio transmission tower. It could be you're very close to the airport and the radio communications between the tower and the airplanes around. It could be radar. It could be a wireless network. Many, many sources of emanated electromagnetic energy in the air all around us. If that signal gets induced into our wires, boom, this is interference. Now, we have this superset. It's called electromagnetic interference. That says, of course, that it uses electron flow and magnetism to push those electrons around. And this is the superset category. This is all forms of this interference. However, there's a subset called radio frequency interference, and a key term here is frequency. If there is any regularity to the interference, it's generally considered to be RFI, radio frequency interference. Frequency being frequently presents itself, and it's sort of some consistent pattern of interference. This is RFI, a subset of EMI, electromagnetic interference. And then we have another subset that is more of a transient noise, a very irregular, staticky, no pattern, no regularity to the electromagnetic interference. So things like a lightning strike, or perhaps we turn on a fan that uses an electric motor and that fan induces some sort of static into our electrical system. This would be a type of transient noise. Again, a subset of electromagnetic interference. This is all bad for your data signal because I want to be able to read my binary ones and zeros out of my signal that's carrying my data. Well, if these signals are inducing themselves into my wires, this is doing nothing but causing confusion and havoc in my attempt to understand my emulated signal and the data that that signal is carrying. We've already discussed emanations to a large extent, but basically this deals with the electron flow through a wire induces or emanates a magnetic field in the air around the conductor carrying the electron. Now that in itself is an emanation. And if it was all by itself left alone in nothing but air or a vacuum, it wouldn't cause us too much of a problem. However, because we have many wires that might be adjacent to one another, like a cable run, a bundle of Ethernet cables running through the walls or through the ceiling, and they're generally packed tightly together, the emanated signal from one wire induces signal interference into adjacent wires because they cross this airspace where this magnetic field is built. So these emanations cause interference and signal degradation. As the second wire gets interference induced into it, essentially that second wire stole energy from the first wire that was emanating. So the signal is being degraded in the first wire due to energy lost in the second wire. And the signal in the second wire is being degraded because it now has electron flow that isn't part of the intended signal. So emanations are a problem in this regard. Further, emanations are the source of data theft. So a bad guy, without actually even touching the wire, can use a detector and sense these electromagnetic fields around the wires and can identify the presence or absence of electron flow, which essentially is your signal carrying the data. So the bad guy can actually steal your data just by sensing these emanated signals into the air. Again, this is a security concern in addition to be a degradation of signal. And as we described these emanations, I also described what is called crosstalk. As I'm sending an intended signal down a wire carrying data, it induces or emanates a magnetic field in the air around that wire. Well, an adjacent wire that penetrates that magnetic field is going to have energy induced into its data carrying signal, and this is called crosstalk. When one wire induces signal, unwanted signal, in the second wire, this is called crosstalk, and this is that degradation of signal and the theft of energy, and again, could be used to steal the actual data. So these are some of our core terms for network media, and these have implications relative to efficiency of transmission as well as the security aspects of the particular media. This lesson covers several more terms related to network media. In this lesson, we're going to be looking at the difference between baseband and broadband media types. Let's first look at baseband. Baseband transmission technologies allow only one signal on a conductor at a time, on the media at a time. And if a second signal is transmitted onto the media while a first signal is present, both signals are destroyed. In other words, the recipients can no longer understand what the data is that the signal is supposed to be carrying. So both signals are destroyed. This is referred to commonly as a collision on a network. So on baseband networks, only one node is allowed to transmit at a time. And if two nodes transmit at the same time, both transmissions are destroyed. Both transmitting stations need to stop transmitting and allow the media to stabilize, and then they can, over time, try to begin to access the media again, hopefully not colliding with somebody else's signal. So we're going to be looking at ways that this may occur later on. Now, one technique to allow multiple nodes to share the same common media for baseband is using something called time division multiplexing. What time division multiplexing does is it takes, let's say, a 1 second period, and it breaks it up into, let's say, 10 different time slices. And it then will allow node number 1 to transmit during 1/10 of that 1 second period. One time slice is what it's called. And then it says, all right, you have to stop. Then it goes to the second node and says, all right, it's your turn to transmit. And now the second node transmit, but the other 9 nodes are not allowed to transmit during that one time period. By using some mechanism of identifying whose turn it is, time division multiplexing allows multiple nodes to share a common baseband media. And the media access methods are commonly used and have been used historically, will be explored in later videos. So some technologies that use baseband are Ethernet. Now, Ethernet, as we said, is probably the single most commonly used network media for all of our networks. We might have long data runs where we use fiber optics or wireless or SONET or something along these lines. SONET would be fiber optic. But within a building, for example, almost all cabling is Ethernet today. So Ethernet is the champion when it comes to our media type. Earlier media types that used baseband transmission technologies were token ring and ArcNet, Advanced Resource Computing Network, or Attached Resource Computing Network. So these two older technologies, token ring and ArcNet, also were baseband technologies where only one node is allowed to transmit at a time. Those last two, the token ring and the ArcNet, are considered to be token passing technology. We'll talk more about that later. Now, the competing technology to baseband is broadband. Broadband is the newer, rapidly growing technology where multiple data signals can occupy the same common media without destroying the other signals. In other words, multiple nodes can transmit simultaneously on one conductor, on one media type. And so this is called broadband. And as you can probably figure out, broadband, because it allows multiple data streams on a single wire, is much more efficient. It has a much higher data rate, and it's used in larger, faster networks. Now, the kicker, though, is typically broadband technologies are more expensive than the baseband technology. If only one guy is allowed to use the wire, of course, it's slower, and of course, the electronics are relatively cheap and easy. But if I need to squeeze 2 or 10 or 20 or 200 nodes on the same wire simultaneously, you can imagine the electronics that support that system are substantially more complex and therefore more expensive. So broadband has substantially higher data rates, more data throughput in the same period of time, but it is notably more expensive. How do we get those different data streams onto the media and not allow them to destroy somebody else's data stream that's concurrently on that same media? We use something called frequency division multiplexing. Typically, this is a radio frequency, which is electromagnetic waves, a radio frequency wave across a coaxial cable. And this allows for one signal to propagate at, let's say, 10 megahertz, and I can send a second signal, let's say 13 megahertz, and a third signal at 17 megahertz, and a fourth signal at 19.2 megahertz, and I use simply a different frequency for each transmitting station, and of course the destination must be tuned to that same frequency. So now what we're seeing is we have electronics that are not just turning on a voltage or turning off a voltage, but they are actually producing these electromagnetic waves, which are sine waves at a specific frequency, but the destination must be tuned to that same frequency, so we have to coordinate all that. And if you have to operate at different frequencies, you now have a very complex transmitter and receiver series to communicate across this same broadband media. Frequency division multiplexing uses different frequencies for the transmitter-receiver pair, but I can put those differing frequencies on the same coaxial cable. So one cable run, and I'll splice out on the destination side to 10 different nodes, but only the nodes that are tuned to my frequency can understand my signal. The good news is I can put 10 or 20 or 200 different signals on that same coaxial cable simultaneously and share that one cable with many data streams. A newer and also very high efficiency and very expensive broadband technology uses wavelength division multiplexing. Now, wavelength relative to the wavelength of light waves. So now we're using photons, not radio frequency electromagnetic energy. We are using optical energy or photons, light pulses across a fiber optic cable. And as we had discussed when we were looking at the different media types, fiber optics are one of your best media types when it comes to efficiency, the ability to carry multiple data streams using wavelength division multiplexing, the lack of emanations, the lack of interference, the greater distances, and the greater security. So this wavelength division multiplexing over fiber optics is the bomb these days. With very high data throughput. The problem, though, is it is notably more expensive, yet still it is notably more secure. All right, all that said, we've covered these two definitions thoroughly, and we will pick up shortly where we left off. In this lesson, we're going to look at Ethernet. Ethernet uses what we call twisted pair cable. It's a total of 8 wires in one jacket and one cable. We take those 8 wires in pairs, and each pair will consist of one wire that's going to carry the data signal, and this second wire is going to be grounded. And then we're going to twist these two wires together. As you can see in the photograph here, we have then 4 pairs of wires that are twisted together. And the grounded wire that's wrapped around the data carrying wire is twisted around that wire so that it will disrupt the electromagnetic field that is emanated as the electrons flow, the signal flows through the data carrying wire. Now this reduces the emanations. It's not terribly effective at reducing it, but it's better than nothing. And it helps to allow the data run, the cable length, to be greater, and we can still have enough signal at the end of the cable to understand what the signal is. So we use this twisted pair cable for our Ethernet networks. We notice that the connector at the endpoint has 8 pins, and it's called an RJ45 connector. So those pins actually are what plug into the back of your computer in the network interface card and plug into the wall jack, which is an Ethernet cable behind the wall, but it's the female portion of this RJ45 connector. And then, of course, those 8 wires connect to 8 pins that are part of this RJ45 connector. Now we have unshielded twisted pair, and that is the single most dominant cable type or media type for networks today. All of our data centers have miles and miles of UTP, unshielded twisted pair. And businesses have this UTP in the walls, in the ceilings, etc., that connect all the offices together, back to the wiring closets where the switches and routers live, and to the data center where all the servers live. So that is almost all Ethernet. Now, there's another form of twisted pair called shielded twisted pair. And on the slide, as you can see down below, the very bottom image is a photograph of shielded twisted pair. And what you'll notice is there are 4 pairs of wires, just like there was with unshielded twisted pair, but surrounding that series of 4 wires is a plastic mylar sheet, very super thin plastic sheet, but it has been coated with a very thin layer of conductive material. So we wrap this, it's almost like a foil. We wrap this foil around the 4 twisted pairs, and then we ground that foil at the endpoints. So this produces an extra layer of shielding around the data carrying wires. So this is our shielded twisted pair. Now, shielded twisted pair has better emanations protection, less signal propagates out into the air around the wires, and it has better protective shielding so that emanated signals outside don't induce so much signal into our wires. And it allows for slightly longer cable runs because of the greater efficiency keeping the energy contained within the wires. However, the cost and the difficulty of using STP is so high, the benefits aren't worth it. So if you have emanations or efficiency concerns, STP typically is not your solution because it's notably more expensive and the benefits are only marginally increased. So UTP is by far the dominant technology. As we twist the ground wire around the data carrying wire more and more and more, eventually if you twisted it very, very much, you would have a ground wire that was completely encasing the data signal wire. However, the problem is that consumes a whole lot of material. You just took a 100-meter cable, and because you twisted it up so tightly, it's now worth 15 feet of distance. You really can consume a tremendous amount of material by increasing these number of twists. Well, studies have shown us how many twists per foot it takes to get a certain level of improved performance out of the twisted pair cables. For standard voice, which is like your telephone cabling, it's called Category 1 cable, and it has approximately 1 twist per foot. In other words, the ground wire wraps around the data wire. The data wire is now carrying your voice data, analog type data, once per foot. And so Cat 1, Category 1, has approximately 1 twist per foot and is generally only used for voice. You notice there's no digital signaling, no data on that other than analog voice data. Category 2 has approximately 2 twists per foot, and it generally is good to conduct about 4 megabits of signal, data signal, over about a 100-meter span. Cat 3 is 3 twists per foot. It gives us about 10 megabits per second. Cat 4, approximately 4 twists per foot, 16 megabits. Category 5, which is where many of our networks were installed, gave us 100 megabits. Today, we want greater data rates, so we're looking at gigabit Ethernet. And now we can either use a very highly refined Category 5 called Cat 5e to get 1 gigabit, but Category 6 was intended as the 1 gigabit per second UTP type of cabling. Now, we have 10 megabits baseband using twisted pair, that's 10 base T. 100 megabits baseband. Remember, baseband says 1 signal per conductor only and ever. If a second signal hits the conductor, we've destroyed the signal. And again, so 100 base T is 100 megabits baseband twisted pair. 1000 base T is 1 gigabit per second baseband twisted pair. There are also cables called crossover cables in Ethernet where these pairs of wires, one pair is typically considered a transmit pair and one pair is considered a receive pair. The cables are built so that the transmitter and receiver pairs are plugged into a hub or a switch, and that's where they connect to the destinations. Transmit connects to the destinations receive. So the crossover occurs in either the hub or the switch, some central connecting device, and we'll be talking more about these devices later on. So the crossover occurs in this intermediary device, a hub or a switch. However, if I needed to connect 2 computers directly together, I would buy a crossover cable that connects the TX directly to the RX on the other side of the wire, on the other RJ45 on the same wire. In this case, my TX pair on one endpoint connects to the RX pair on the other connector, and vice versa. My RX connects to the other end's TX. So the crossover occurs in the cable because there is no intermediary device like a hub or a switch. Now, there was another area of concern relative to the jacketing on these cables. Historically, PVC, that's polyvinyl chloride jacketing, is used. And by the way, that's what almost all of our cables are today. However, the problem is it burns at a relatively low temperature, and when it burns, it emits poisonous fumes that will kill people. For fire safety, if there are concerns about the jacketing of the cable, that if it burns, it's going to injure people, there is a jacketing that uses a different chemical that burns at a much higher temperature, and therefore the toxic fumes are not quite so prevalent with a standard fire. And this is called plenum-rated cable. And it really, plenum-rated simply says we use a different chemical for the jacketing, but that chemical burns at a much higher temperature. In other words, it doesn't emit those toxic fumes when it burns so readily. And typically this is what is used inside the walls or in the crawl space if there is a high risk of fire. So this plenum-rated cable is notably more expensive, therefore not commonly used, and in most cases we've come up with solutions where we don't need to buy the plenum-rated cable versus our standard Ethernet cabling. In this lesson, we're going to be looking at the wireless media transmission technology. Just an introduction, we've got a whole section on wireless later. So in wireless networking, the Institute of Electrical and Electronics Engineers defined a specification for wireless local area networks, wireless LAN as they call it. And that specification is defined as 802.11. So the 802 series deals with communications over networks, and the 11 series, 802.11, says wireless networks, wireless local area networks. So that's where this specification comes from. Now, they define the electronics and the radio frequency transmissions, the frequencies that have been allocated by the FCC are utilized and built into these specifications. Signaling schemes, the way we modulate and encode the data into the radio frequency energy that is propagated out into the airwaves as the wireless signal. This is all defined by the 802.11 specifications. Now what happens then is the manufacturers of wireless access points and wireless network interface cards, they have to interpret those specifications and then implement them in their electronics and the software that controls those electronics. They have to build these radio transmitters and receivers using specific types of antenna that meet the specifications. Frequency controls have to be in place. And so the vendors of the wireless components have to meet these 802.11 specifications as defined by IEEE. And of course, the FCC allocates specific frequency ranges for these wireless networks. Now, the great thing about wireless networks is they are easy to install and they're inexpensive. Why? Because you don't have to buy any cables. You simply buy an access point. Now, you do plug the access point into the Ethernet network, but then the signal is propagated from the access point out to the wireless clients using the airspace. And as a result, there's no need for cabling. So it makes it very efficient. Your users can relocate from one cubicle to a different cubicle. They can go from their office to the conference room, to the break room, whatever they want, and they can still stay connected. This is called roaming in the wireless network. It's a very fast and efficient way to get nodes connected to the core network that is wired. This would be where your servers are, where the resources live, the file servers, the other resource servers, perhaps connectivity to the internet. So we'll connect wirelessly between the laptop, as we see in the slide, back to the access point. And then we use a wired network from the access point back into the core network to get the resources and perhaps even internet connectivity. This is how the wireless network operates. Because the wireless emanates its data signaling into the air, it is least secure. In other words, a bad guy simply has to fire up his laptop and he can eavesdrop on every transmission that occurs between the access point and the client nodes. And it also is most susceptible to interference from other radio frequency sources. So we have these problems that we have to deal with. This is one of the reasons why there are power limitations in those 802.11 specifications that say your access point can only propagate at this power level, trying to contain physically the space that you are emanating your signal into so that you don't somehow interfere too heavily with the wireless networks adjacent to yours, on the floor above and on the floor below and on the offices through the wall. These power specifications in 802.11 specifications help to control that and keep the size of the propagated cell, as it's called, to what we would consider to be a functional local area network, and hopefully not much past that. Again, the primary hardware associated with the wireless network is the access point that typically gets a Ethernet cable attached to it back into the core network, but then it is the connection point for all the wireless clients within its cell. So the cell is the area of radio frequency propagation, physical space, and all the nodes that are associated to this access point. So that's the definition of the cell. We'll be looking at wireless networking a lot more in a later section in this series of lectures. This lesson covers modulation and encoding. Now, this modulation and encoding happens at the physical layer, down at the network interface card, and at the network interface card on routers and on other systems like switches perhaps. So modulation and encoding is essentially this: the encoding of your binary data in a modulated signal that is appropriate for the media. So let's consider fiber optic cable. A fiber optic cable uses photons to carry the signal, and the signal carries the data. So we could say that if I modulate the light by turning it on to encode a binary 1 and turning it off to encode a binary 0, we have just introduced digital unipolar modulation and encoding. Turn the light on, we have a binary 1. Turn the light off, we have a binary 0. The turning on and off of the light is the modulation. And the encoding is the representation that light on equals 1, light off equals 0. Here we've just identified digital signaling. It's either a 1 or a 0. It's not analog. And it is unipolar. In other words, we have two states. It's either on or it's off. So this is a very basic, fundamental modulation and encoding technique. This again is digital signaling, and it's unipolar because it's either on or off. Now, our Ethernet media also uses this digital unipolar signaling as well. And it uses, instead of photons, it uses voltage which pushes electrons. So electron flow and voltage are the mechanisms that convey the data signal inside the media that is Ethernet. So with an Ethernet network, we use plus 3.3 volts DC to represent a binary 1, and 0 volts, or the absence of voltage, to represent a binary 0. And I can use this 3.3 volts to modulate the voltage from 0 to 3.3 volts to encode my binary 1s and 0s. Now, I say that Ethernet uses digital unipolar signaling. There are many signaling schemes, and there are some variations on this. So this is an example. It is not necessarily a lot. There is also a bipolar signaling scheme. And in my example here on the slide, I'm referring to what we would use over a T1 connection, for example. That's a long-distance signaling scheme used by the telco systems. So back in the days before we had such great internet connections from coaxial cable or fiber optic broadband or whatever you're using today, back in the day, the way we had to connect our offices together was we would pay the telephone company for a dedicated set of wires between the home office and the branch offices. And it used T1 technologies, Telco 1 technologies, which used plus and minus 120 volts to convey its signal. And this was called digital signaling, but it was bipolar. In other words, I could be plus 120 volts to convey a digital 1 or minus 120 volts to convey a digital 0. And the good thing about this is, if you notice, in between each binary bit, there is a return to 0 state. In other words, two 1s in a row are clearly delineated because I send you out a binary 1 at 120 volts, but then I return to 0 volts for a period of time. And my second one is coming, okay, here it comes, boom, there's the next 120 volts to convey my second binary 1. Now, over a long distance, those binary 1s are going to attenuate. They're going to degrade. And over some distance, it's going to get to a point where the receiving side is struggling to figure out, was that a 1 or was that I'm still at 0? I can't even tell. And so that's why we did this return to 0 for the definition of a 1 bit, and now that 1 bit is done. And here comes the second 1 bit, and now that 1 bit is done. And then we drop to minus 120 volts to represent binary 0s. So this is bipolar digital signaling. And again, this is just one example of the many forms of bipolar digital signaling that can exist. But this example is roughly out of the T1 era of signaling over long distances. So we use much greater voltages so I can afford a lot greater attenuation because my data runs are so much longer. Now, the third modulation and encoding scheme that we have here is analog signaling. So we had two digital signaling schemes, unipolar and bipolar. Analog signaling uses radio frequency waves to conduct its modulation and encoding to get its binary data tucked into this radio frequency signal. Now, analog signaling, as we said, uses radio frequency waves, which are electromagnetic, and they can propagate wirelessly into the air. It's reasonably efficient to send this radio frequency signal into the air, but we also can send that radio frequency signal through some coaxial cable as well. So the coax can be used for either digital or analog, but the digital cannot be conveyed over wireless. Analog signaling can be used over coaxial and wireless through the air. and is not really good on Ethernet cabling, the other form of media that we were discussing earlier. Now, how do we modulate and encode signal using analog signals? Well, I have got several forms here. The first one is called AM, or amplitude modulation. As we look at that signal over to the right next to the analog label, we see that it has a certain height. That sine wave goes a certain height up. Now, the height of that wave is an indicator of the power or voltage that's applied to create that wave. And what I can do, if I want to encode a binary 1, I can make that wave taller. In other words, I'll use greater voltage, greater power for that one part of the cycle to encode a binary 1, for example. And if I want to encode a binary 0, I will decrease the voltage below the carrier signal that we see there. So a lower power will represent 0 as the encoded signal. And I'll modulate the voltage or the power of this first portion of the sine wave, either higher or lower, to encode a binary 1 or 0. That's amplitude modulation. Frequency modulation says use a higher frequency, would be a shorter wave, to represent a binary 1, and use a lower frequency, a longer wave, to represent a binary 0. So here's another way I can modulate the frequency to encode binary 1s and 0s. Higher frequency, shorter wave equals a 1. Lower frequency, longer wave equals a 0. Now I also can use something called phase shift keying, PSK, and this says where that one sine wave completes, if I continue upward as it's supposed to, as we see in the diagram, that represents no shift in the phase, and that would be a binary 0. But suppose I inverted that wave now 180 degrees. And instead of carrying upward forward as my sine wave continues, suppose I reverse that wave and I go down for a half a wave. And by shifting the phase 100 degrees, I can represent a binary 1. Or if I don't shift the phase, I represent a binary 0. So here is a phase shift keying, another technique for modulating a radio frequency or analog signal wave and encoding binary data bits. This last one, quadrature amplitude modulation, QAM, this is what's used on the bulk of our wireless access points and our wireless network interface cards. It's a combination of amplitude modulation and phase shift keying, and it allows us to encode as many as 64, or the newer QAMs will modulate and encode up to 256 binary data bits in a single sine wave. Phenomenal amount of data packed into a single sine wave. So this is how we're getting these substantially higher data rates, one of the techniques we use to get these substantially higher data rates on our wireless networks. So this lecture has been on modulation and encoding. We're going to break here and we'll pick up with some new stuff when we come back. Let's continue with the review of network topologies. Now a topology is a construction, if you will, or a type of construction. And in this case, it's relative to the structure of our networks. Let's first start with the bus topology, because this was one of the original topologies. This came to us out of classically the 10 base 2 and the 10 base 5 type of networks that used a linear bus topology. Now this is a core backbone, that's the bus part of this, that we would snake through the office, if you will, and then you would tap into that bus, that backbone, with the different nodes that you want to connect to the network. Now the linear bus has the problem that it requires terminators at the endpoint, because here's what happens. As a node on the bus begins to transmit, the energy that is the signal, now this is electron flow pushed by voltage, we're pushing electrons, this electromagnetic energy, this electron flow, will propagate in both directions from that transmitting node on the bus. And if the energy hits the end of the cable and is not properly terminated or destroyed or absorbed, then the energy will reflect back into the cable and begin to destroy the oncoming signal. You remember baseband technology, that's what this is. A baseband technology can only tolerate a single signal on the wire. And if two signals enter the wire at any point in time, both signals are destroyed. Well, that reflected signal is a second signal now on the wire. What we'd have to do is add terminators to the ends, the two ends of the linear bus network. Now, here was a continued problem with this, and that is that if any connection came loose on that linear bus, we now have two halves of a bus. One end is terminated on each half, and the other end of each half is now not terminated. And as a result, we would get that reflected signal due to this unterminated endpoint, and each half of the bus would now be down or non-functional because of this constant collision status. This would cause a constant point of aggravation and constantly needed to be repaired. You'd always be wiggling connectors to make sure that you've got a solid connection on the linear bus. Again, 10 base 2, 10 megabits baseband, 200 meters was the approximate length. About 185 meters was the actual length for 10 base 2. That was called thin net, and then thick net was 10 base 5. It was a fairly large coaxial cable was the backbone that ran approximately 500 meters. About the consistency of a frozen garden hose that you tap into as the backbone or the bus for this network. Now, the next topology we're going to look at is the ring topology, and this was championed in primarily the token ring type of networks. In this case, the coaxial cable switched over to Ethernet type of cable. The token would run from one node to the next downstream node in the ring. So the token would pass from one node to the next, to the next, to the next, and eventually commute the ring. And this was a token passing technique, but the network topology was a ring topology. Now, the next one we're going to look at is called the star topology. The star topology is what we use primarily today on our corporate networks. We wind up with this central connection block. Now, back in the original days, this was really nothing more than a connection box. Basically was a series of wires soldered together. There was no power to it. There was no repeater function in it. There was no intelligence whatsoever. It basically connected wires together, and the various nodes would then be able to communicate amongst one another. However, in time, these connector blocks became powered and were amplifiers or repeaters, if you will. In a digital sense, we would call that a repeater. So in addition to it having all the right connections so that different nodes could communicate amongst one another, that central point that required power was also a repeater that would regenerate the signal. And this formed a star topology because the different nodes would each have to have a cable run back to this central hub or concentrator. Now, today, those hubs have been replaced with switches. However, similarly, each node must still connect back to the switch with typically a dedicated Ethernet cable run. So we still typically today rely on this star topology. The next one we're going to look at is called the tree topology, and this is an extension of the star, if you will. This also could be considered a hybrid topology because it's more a combination of the bus and the star. So here we have the tree topology that has something akin to a backbone, a core, typically high-speed, high data rate backbone that you would snake perhaps up the elevator shaft, and then you would tap off of that backbone on each floor with a star. And so each floor then would be a branch on this tree, with the trunk of the tree being this perhaps fiber optic cable run that would run up the elevator shaft. So this was a sort of a hybrid or a combination of the bus and the star topologies. Now, in this case, if the backbone were to have a failure, then each floor, each branch on that tree would still operate correctly. So we'd have still a functioning local area network for that one floor, but it might not be able to communicate with the other floors in the example that I described. Now let's roll back and let's look at that star. Well, what happens if the concentrator or the hub or the switch in that star fails? So the hub, concentrator, or switch is the central point, the main point of failure. Because if a node goes down, no problem, the rest of the network operates fine. If an Ethernet cable fails, only that one node is affected by the bad Ethernet cable. The rest of the network is fine. So the concentrator itself, or the hub or switch itself, that middle point, is the single point of failure that would bring down the network. On the ring, very similar to the bus, if the ring network ever became disconnected, then the network would be down because the token could no longer commute the ring. So the ring network, the cable itself is the point of failure, just like on the bus, the cable itself is a single point of failure. Trying to defeat this notion of a single point of failure is the reason for the next type of network, the next topology, and that's the mesh. The point of the mesh network is to have redundant paths, and that way if any one cable or device fails, the rest of the network can operate correctly because it didn't rely on that one device or that one cable run for connectivity. There were multiple paths to each destination. Now, the notion of the full mesh is more of an academic model because it typically is greater redundancy than what's really needed, and that increased redundancy comes with a price. And so typically, if you had a second path, a redundant path from point A to point B, you're already great when it comes to redundancy. And you don't need 5 paths because the cost of those 5 paths are way too expensive. So typically that full mesh is more of an academic model and typically not implemented. Therefore, the partial mesh is typically the type of model that has been implemented. Now, the difference between a physical topology and a logical topology primarily comes in the ring topology, because in the early token ring networks, the cable literally was constructed to form something akin to a ring, and the token would pass or commute from one node to the downstream neighbor next node to the downstream neighbor next node and would eventually make the entire loop. However, as token ring networks became more and more popular, a concentrator was built so that token ring would actually exist inside the concentrator, but each node would have to have a cable back to the concentrator. So in this case, we had a physical star. The cable runs physically produced a star topology. However, the token passed in a ring topology, but the ring was pretty much collapsed within this central concentrator. By the way, the name of that concentrator was a multi-station access unit called a MAL or an MCell. We're going to take a break here after reviewing these network topologies, and we will pick up shortly where we left off. In this lesson, we're going to explore the different sizes of networks. This has to do with a little more than just size, though. It has also to do with the level of administrative control and trust. These are some of the aspects we're going to be looking at in this particular description or discussion. Let's first look at this term intranet. This is a collection of well-connected segments. A segment is a network that is bounded by a router. In other words, from the router out to all the nodes that connect to that point on the router, that's considered a segment. And the router can connect multiple segments together, and multiple routers can connect multiple segments together. So this intranet is typically private and has well-connected segments. Now, very often, we will describe the intranet as the network that your computer is connected to, because there's this contrast we're going to bump into when we look at the next term. So consider that this is the network you are connected to. Now, very often, because today data rates are getting higher and higher, you might have a connection to a branch office, let's say, that uses gigabit fiber optic. And as a result, this well-connected notion may fall apart a little bit. So we're going to add 2 other types of boundaries that establish what we might consider the intranet. And so first, it's this private, well-connected, land speed or better, collection of segments. However, if you have different administration, in other words, a different team is administering the computers on your collection of segments versus their collection of segments, like a headquarters and a branch office with a gigabit fiber optic connection between them, we might consider that because of this different administration, these are different intranets. So this administration, this control and level of trust might define a boundary of your intranet versus their intranet. And yet another component that might tend to be this boundary is security devices. So we have common administrative control and policy. That's one boundary that we might use as our definition of intranet. We have a lack of trust, which is typically going to require some sort of security device added as a boundary, like firewalls. This might be the definition of your intranet. You live on the inside where it's all trusted. Anything outside those security devices are less trusted, therefore not part of your intranet. And finally, we have this original definition that's now kind of getting a little fuzzy because of the high data rates on our metropolitan area connections, regional area connections, and perhaps even wide area connections. This well-connected segment might be skewed a little bit because of these high data rates that we're getting now on our larger or longer runs. To a large extent, it now deals with a level of trust, administrative control, and connectivity. And typically, it is a private entity that holds, controls, or defines policy on this intranet. Now, in contrast to the intranet, we might have a second collection of well-connected segments that we don't trust so much. However, we're connected to it persistently. So this is the classic definition for an extranet. Here we have a less trusted collection, one or more segments that we connect to on a regular basis. Where my computer is attached, it's my intranet. However, I still may have a good connection to this other collection of segments, but that is now my extranet. And the extranet is less trusted, perhaps managed by a different administrative staff, and might be bounded by a firewall or some other security boundary that allows me to filter and limit their access to our trusted environment on our intranet. Now, the extranet has this mid-level of trust and control and connectivity. Even though it still might be that 1 gigabit connection to the branch office, we still consider that that's more of a WAN link and not part of our local area network, our intranet. And finally, the third definition here is internet. Well, that is that big global network that holds all those web resources, the web servers, the FTP servers, things along these lines. Now, that intranet is the public space, and that public space is the least trusted, has the least amount of control from my perspective, and therefore we generally will want to defend ourselves very rigidly from the outsiders coming into my intranet from the internet because of their exceedingly low level of trust. We're going to move forward and we're going to address a little bit more the size of the network. So here's a handful of definitions that tend to describe in physical space how big is the network. We'll start with the smallest and move towards the largest. The first is the personal area network. Now typically this is about a 10-meter radius. 10 meters is about 33 feet, and therefore this is a fairly small network. So the PAN, or personal area network, primarily will use wireless Bluetooth technology for most of our computing devices, but there's this low power wireless technology called Zigbee that is very similar to Bluetooth, but it focuses very much on exceptionally low power. So we have very low battery requirements for Zigbee technology, but Bluetooth right now is the dominant technology. Zigbee is coming along, though, in many, many marketplaces. The next one up is local area network. We're talking about tens of meters to hundreds of meters of geographic space. And typically, we use Ethernet cabling and wireless networks. This would be our wireless LAN, your typical access point running 802.11a or B or G or N, or the new standard is 802.11ac. And these are our wireless local area networks. So we're talking hundreds of meters that we might string together. And this produces our LAN. And that LAN, of course, as we just described, is kind of like your intranet. Now, the next one down is called a metropolitan area network or a campus area network. And here we're going to take these LANs and we're going to string them together And we're going to get hundreds of meters to miles to maybe even tens of miles of space out of the metropolitan area network. Typically, these LANs will be connected by fiber optics or perhaps wireless point-to-point connections. And they typically are a metropolitan area network because they have a common administrative force or policy. And that's what makes it a collection of LANs that are connected together. Next one down is regional area network. This typically will run tens of miles and again will run fiber optics and point-to-point to connect perhaps several metropolitan area networks together. The next one down is the wide area network that will run tens of miles to tens of thousands of miles. And this would be what our internet network is like. It is a wide area network. At the same time, the internet is also a global area network. So you can have a private corporate wide area network that is not the internet, but it still may be a global area network because it spans the globe. This wide area network and global area network, they're very similar. However, with some subtle differences, you could have a wide area network that doesn't span the globe, but you then can also have a global area network that does span the globe by definition. So these are sizes of networks related to networking technologies and media. We'll take a break here and we'll pick up shortly. In this lesson, we're going to be looking at different network transmission types. Now, these different network transmission types are defined by the way the network stack and the application that feeds the data into the network stack chooses to communicate with one or perhaps multiple nodes on the network. Now, the first example is called the unicast. The unicast is from a single source to a single and unambiguous destination. This is a one-to-one data transmission or flow of information from one point to a specific single point as a destination. Now, this is typically performed by transmitting from a class A, B, or C IP address to a destination class A, B, or C IP address. However, it is also possible to communicate or to send out a unicast to an unambiguous and unique MAC address. However, I'd say that's not as common as from a single IP address to a single IP address. So a unicast is from one node to a specific single destination node, and this is the way many of our network communications occur today. Now, the next one, broadcast, is performed to accomplish sort of network administration. Most of the time, you don't send the actual payload of data in a broadcast, but the broadcast is typically done to achieve some information or acquire some information that is needed to accomplish the flow of data, not actually to perform the flow of data. So a broadcast is typically sent from one node, the transmitter or the sender, to all the nodes within a specified range. And that range is defined typically by the layer 3 address or the layer 2 address that is supplied in the outbound broadcast. Now you can have a layer 3 broadcast that uses an IP address with the broadcast address for the subnet that you're sending the broadcast to. So that would say all people with an IP address that start with 192.168.10, I'm transmitting this to each and every one of you. So what those nodes would do is every node that hears that broadcast looks at their IP address, checks to see if they're at 192.168.10. something, and if they are, they say, oh, this broadcast is for me, and they process this up the stack to layer 4. They still may discard it at the higher layers, but at layer 3, the expectation is that they will process this packet and hand it up to the higher layers. Sometimes we don't have the IP address information, and we can't use the layer 3 broadcast. In this case, we'll use a layer 2 broadcast where we use the broadcast address for the media access control layer, the MAC address. we're going to, in this case, for a layer 2 broadcast, supply the broadcast address at layer 2, which is all binary ones. However, if you recall, MAC addresses are typically documented or written by using pairs of hexadecimal characters. And in this case, all ones, the broadcast address, will translate in hexadecimal to all Fs as the MAC address. Now, if you're going to send a broadcast at layer 2, you may or may not be sending a broadcast at layer 3. But if you're sending a broadcast to layer 3, you are always sending the broadcast at layer 2. So a layer 2 broadcast may or may not be a layer 3 broadcast. A layer 3 broadcast will always be a layer 2 broadcast. And basically what you're saying with the layer 3 is everybody within this IP subnet, I'm talking to you. The layer 2 broadcast says everybody on my segment, I'm talking to you. And so here's the difference between the physical segment and the logical address space or spaces that might be assigned to that single segment. The segment is a physical thing. That's the collection of all nodes bounded by a router. However, on that one physical segment, I could have one or more logically addressed IP subnets. That's the assignment of IP address space on that one segment. Then I could have one subnet or I could have multiple subnets on that one segment. The segment is a physical construct. The layer 3 address space is a logical construct where we can type in any numbers we care to on the configuration of those nodes that might all be connected to the same single segment. Now the next one down, transmission type down, is called the multicast. The multicast is from one node, the source server or sending server, to many nodes that have opted in for this particular multicast transmission. Multicast is defined by the Internet Group Management Protocol and has been allocated a special Class D of the IP address space. Class D IP address space, the first octet number starts at 224 and ranges up to 239. So any IP address that begins with a number between 224 and 239 inclusive, this is a multicast address. And with this one multicast address, I might assign the address to 10 nodes or 10,000 nodes, the same IP address. Let's pick a number. Let's say 230.1.1.5. I can assign that Class D address, that multicast address, to a large number of nodes that I want to send my multicast transmission to. And then from my source server, the one server, I'm going to send out a single data stream to that same IP address, 230.1.1.5. And then every node that has that IP address bound to it is supposed to receive this transmission. It's the routers in between that transmitting server, that source server, and all those destination nodes that have the same IP address bound to it. The routers perform a duplication and distribution process to duplicate these frames. Because I'm only sending out one stream, I'm sending out one frame, the routers have to duplicate it to be sure everybody who's opted into this multicast transmission receive a copy of the frame. And this is multicast again using IGMP, Internet Group Management Protocol, and again uses that Class D IP address space of 224 to 239. The opted-in part could be nothing more than you come to my webpage and say you want it, or I might make you authenticate because I only want to send this to my employees, not my competition. So the opted-in can have different levels of security, or perhaps I'm selling you this movie that I'm going to be transmitting, and therefore I need your credit card. I need to hear a cha-ching sound before I let you opt in to my movie transmission. And in that case, once you pay me, then I'll give you the IP address that I'll be transmitting this information to, this movie to. The last one on the list here is called Anycast. Now, this guy hasn't gotten much business yet, but the notion behind the Anycast is we will send a frame from one sending node to one of a set of nodes, and that set of nodes are typically providing a common service. Let's take, for example, DNS, the domain name system. Now, in a corporate environment, you might need one or multiple DNS servers to provide failover and redundancy capabilities. In other words, if one DNS server is down, I don't want to shut down my company. I'll have multiple DNS servers available on my corporate network. So what I'll do is I'll provide an Anycast IP address to all of my DNS servers, and when a client, the one, is looking for the DNS service, he sends his request to the Anycast IP address that is bound to each and every one of those DNS servers. Now, the first one of those that responds to this request satisfies the need. But if the nearest one happens to be down, that's okay, because one of the others that have this same Anycast address will receive my request and will be able to respond to me, maintaining the availability of this particular service. As I said, we haven't been utilizing the Anycast type of transmission yet. However, it may increase as we move heavily onto IP version 6. This is going to conclude our lesson on network transmission types. We'll pick up shortly where we left off. Let's take a look at media access methods. This occurs at layer 2 of the OSI model, the data link layer, and this is where the data link layer is ready to begin transmitting the frame. That's the completed string of binary ones and zeros that is everything that's required in order to commute this information from the source computer to the destination computer. It's the entire completed frame that has layers 2, 3, 4, 5, 6, and 7 of the header, the payload, and typically a CRC trailer. Now that's a standard Ethernet frame. That's a standard construction for an Ethernet frame. That's what we're going to be generally using as our example, because that's largely where our networks operate. When we have a shared media, that would be like Ethernet or wireless, we have to be concerned about collision, because these are typically baseband networks, which means if two nodes start transmitting at the same time, they will collide. The second transmission will destroy both transmissions, and as a result, nobody's accomplishing anything. You have to stop the network, and then slowly the nodes will begin trying to merge onto the media without colliding again. So because most of our networks are baseband today, we have to find a way to merge these frames onto the wire, the media, without colliding. And that's what we're talking about, media access methods. Now, historically, mainframe computers were the only intelligence on the network, and they would be communicating with many different dumb terminals. Thin clients or dumb terminals. These were the two names for the workstations where the workers were that were accessing the intelligence, the programs, and the data that were existing on the mainframe computer. So back in the day, there was only one box on the entire network that had any intelligence, and that was the mainframe. And so the way the mainframe would manage the media access is the mainframe, the only guy with any smarts, would poll the different thin clients or dumb terminals and say, node number 1, do you have something to transmit? No, you don't? Okay. Node number 2, do you have something to transmit? Oh, you do? Okay, tell me, stop. Node number 3, node number 4. And it would simply poll each of the workstations to see if any of those workstations had something to transmit or not. Now, this was terribly inefficient, because you'd have 4 nodes out of 20 that had work to be done, and the other 16 had no work to be done. And as a result, the polling process would occupy time, in this case, 4 out of 5 times polling a workstation that had no work to be done. So it was a waste of time. Terribly inefficient. We don't use it much today. Later technology was token passing, and this was the ARCnet was a token passing network, and token ring and token bus were 2 other forms of token passing network. And in this case, typically the first node on the network would be called the token master, and its job was to put one and only one token on the network. Then that token would pass from one node to another, to another, to another in some sort of programmatic process or sequence, and only the node that was holding the token would be allowed to transmit. All other nodes were not allowed to transmit. So this was another way to avoid these collisions. Polling and token passing were called deterministic media access methods, because it is determined absolutely who's going to be transmitting, and there is no contention for the wire. There's no possibility of a collision on the media. So these were deterministic and contentionless media access methods. However, there's an awful lot of wasted time with these two different technologies for accessing the media. Where we have evolved is primarily using carrier sense multiple access collision avoidance or collision detection, CSMA-CA and CSMA-CD. Now we're going to take a closer look at these two different media access methods. These are the ones that we use primarily today on our local area networks and then some. Now the first one we're going to look at is CSMA, Carrier Sense Multiple Access Collision Avoidance. This was used in the early AppleTalk days because early Ethernet networks were half duplex. In other words, a node could either transmit or a node could receive, but could not do both at the same time. So when a node is transmitting, it could not tell if there was a collision. And if a second node started transmitting and collided, both nodes, since they're both in transmit mode, would just continue transmitting, wasting time on the network, and as a result, terribly inefficient. So we shifted away from these half-duplex networks to full duplex that were much more efficient and allowed us to get away from these collision avoidance techniques, which also increased the higher overhead. Now, our early wireless networks also operate in half-duplex. In other words, they can transmit or they can receive, but they can't do both. So the early 802.11, 802.11b, and 802.11a and g all operated in CSMA-CA collision avoidance with the higher overhead. Let's look at the timeline of how this CSMA-CA operated. First, we would have a contention period where anybody could transmit, but coincidentally at the moment nobody is transmitting. So a node would listen before talk, would wait, that's a clear channel assessment, and if it senses that nobody is transmitting, it would send out a tiny little announcement frame. Now, the reason it was tiny is because something that small is hard to collide with. It's harder to hit something that's tiny than it is to hit something that's big. So send out a tiny little announcement frame and hope you can get it on the wire before somebody else collides with it and destroys it. And if you can get your announcement frame on the wire, media I should say, then we have this little bit of a wait period to make sure nobody collided with it, but then you have reserved the media for the duration, whatever your announcement frame declared. Now we've moved into a contention-free period, and only you are allowed to transmit because only you had that announcement frame successfully announced on the media. So now you'll transmit your frame, and in wireless, we have a positive acknowledgement for each transmission. So after you transmit your frame, there's a short wait period so that we let the airwaves settle. And then we have still a reserved period for the recipient of that frame to acknowledge receipt of the frame, a short little wait period after that to let the airwaves settle, and then we move back into a contention period where anybody can transmit. So this is the nature of CSMA-CA, with the early announcement frame, a wait period, and then at the tail end of the frame, a wait period, a positive acknowledgement, and another wait period. Those announcements and wait periods and acknowledgments are all not productive time. I'm not actually sending any worthy data. This is all just overhead. So this isn't the most efficient technique. However, because we were operating in half duplex, this was the best we could accomplish to try and minimize the collisions. In contrast to CSMA-CA, we have CSMA-CD collision detection. This is where we recognize there is a potential for collisions, but because we're running now in full duplex, I can sense a collision the moment it happens. So here I am transmitting, somebody miscued and starts transmitting while I'm transmitting, boom, we have a collision. Both data sets now, data streams are destroyed, but because we are running in full duplex, we both can recognize, oh my goodness, we have a collision, stop transmitting, let the dust settle, and now slowly we'll begin this contention period again and we'll start transmitting again. So because we're full duplex with Ethernet, our newer Ethernet, as of about mid to early 1990s, most of our networks started shifting towards full duplex. Because we can sense and transmit at the same time, we can operate in collision detection. Our newer wireless networks that use multiple transmitters and multiple receivers that can sense and transmit at the same time, 802.11n and 802.11ac using this multiple input, multiple output or MIMO technology, can sense and receive. Therefore, they can operate in full duplex. It's up to the vendor that builds these how they actually implement these access points, though. They could potentially run in CSMA CD. So here's the way this guy works, and it's a lot simpler and a lot more efficient. We start with a contention period where anybody could be transmitting. And if I have something to transmit, I do my clear channel assessment. This may also be called a listen before talk. And I sense the wire media and see if anybody's transmitting. If nobody's transmitting, I simply start transmitting my frame. And because I could sense a collision, I'm okay continuing to transmit because I'm not blind. But if everybody's behaving themselves, my frame will complete correctly. And as long as each node has heard my transmission of my frame, they know not to talk because their clear channel assessment will say, no, the media is busy. So we have a contention-free period for this time. Then after my frame is complete, there's a little wait period, a little fixed period where we're letting the dust settle, if you will. And then finally we roll into a contention period again where anybody else could sense the media and potentially transmit their data. So these are our media access methods. We talked about polling, we talked about token passing, we talked about carrier sense, multiple access collision avoidance, and finally carrier sense multiple access collision detection. We'll take a break here and we'll come back with our next lesson.